Thanks so much for coming, and with that, we'll start with Mike.
Thank you. Following up with Stephanie, when I was a kid, we lived in Devon in the southwest of England, and my dad had a hotel there, and we were generating our own electricity with a water wheel in the street. So,
We need to hear you better.
Oh, shall I use this? Yeah, so can you hear me better?
Yeah.
All right. So yeah, we generated our own electricity, and sometimes the lights would flicker at night because leaves were clogging the wheel, and my dad had to go out and start to put a petrol engine in. Emergency thing. Anyway, I'm going to talk, as you've seen here, about some of the great women physicists and astronomers in history, before Marie Curie and in the last century. Before I came to Fermilab 28 years ago, I was at Stockholm, where I was professor there, and before I left there, I was working on ideas to find the Higgs boson at the Large Hadron Collider. I dropped that ball, came over here, and joined in finding the top fork, and then after the Tevatron closed, then we moved over to the Large Hadron Collider, and that's me in the tunnel there, where we eventually found the Higgs boson. But that's not this talk. So this talk is encouraging girls, young women to do science. If you like it, go for it. Or whatever you like to do, go for it. It could be dancing, music, writing, whatever. And if you're lucky, somebody will get you to pay for it. Pay for it. And I have the column in the local paper, Positive in Naperville. This link site takes you there. It's about 30 columns. And in November 2018, I wrote one specifically titled like this. And that was inspired because, apart from it being very topical to get girls and young women into science, the Nobel Prize for 2018 in physics was given to Donna Strickland, one of 3 prize winners who broke basically a 100-year drought of women prize winners in physics. For a period of 100 years, only 1 woman got the Nobel Prize in physics. And over 100 men, I don't know how many men got it, but do you know who knows who and why that 1 woman was?
Madame Curie.
No. It's after Madame Curie. Madame Curie got it in 1903. After Madame Curie got it, it was over 100 years when only 1 woman got it. Does nobody know who it is?
Leona Woods?
Huh?
Leona Woods?
Who was the woman who got the only Nobel Prize in the 100-year period? I'm going to tell you, but I thought you might not know. She's not so well known, but several women deserved it, of course, and that's more to do with the male-dominated culture of physics in the 20th century, rather than women's ability, although it's true to say that not nearly as many women were doing physics as men were. But of course, don't be motivated to do physics by the dream of a Nobel Prize, because you're not likely to get it man or woman. You have to be motivated by the love of the subject, and your enthusiasm, excitement being part of search for new knowledge. And if you're lucky, you will see something that nobody ever saw before, or you'll understand something that we understood before. So it's fun, privileged to be part of it. Of course, there are times when it's not fun, frustrating, you can't get something done, you have problems with your colleagues or something like that. It's not 100%, but it's still fun overall. Find what you love to do and do it. And if you're interested in the subject, it makes no difference if you're any genders, the whole spectrum are equally good. This was the 1 woman who got the Nobel Prize in the 100-year period after Marie Curie and before Donna Strickland last year. Maria got the minus. She discovered the shell structure of the atomic nucleus in the 1950s. She got the Nobel Prize in 1963. She shared it with 2 men. She was a volunteer researcher at the University of Chicago in the 1940s. Her husband was on the faculty, and they had a policy, apparently, of anti-nepotism, not having couples both on the staff. Whether that's the reason, I'm not sure, but she was turned down at Columbia and Johns Hopkins, 2 other prestigious universities, but she got a part-time job at Argonne National Lab, which was associated with the University of Chicago. And while she was doing that day job, in her spare time, she made brilliant and groundbreaking discoveries about the structure of the atomic nucleus, the nuclear shell structure. Then she was quickly hired as a full professor at the University of California in San Diego. She got the Nobel Prize only 3 years later, having been nominated in 2017 times in previous years, apparently. So what she did, she looked at all the nuclear isotopes. You know, the atomic nucleus is a little tiny ball of protons and neutrons stuck together with a strong, really strong force. Protons are red, neutrons are blue, you all know that. And the especially stable nuclei seem to have magic numbers, 2 protons, 8 protons, 20 or 28, the same number of neutrons, 2 or 8 or 20. These seem to be magic numbers, and they're called magic numbers, that made nuclei particularly stable, but nobody knew why. So magic is real. She got the Nobel Prize for understanding magic. This was 2 weeks ago. I was in Las Vegas at a conference on skeptical thinking. There I met Penn, and then I met James Randi, so we got pictures taken with Penn. So magic really is real. This is her getting a Nobel Prize for the King of Sweden in 1963 with King Gustav Adolf. When I was in Sweden, I actually got to know the Royal ceremony once, and that was really great to see the royal family and all the, call it Penguin Mountain, all the Nobel laureates in their penguin suits up there. Does anyone know what this is? Right. She used slide rule. We have calculators there. Okay. So she did the slide rule.
What is it? You couldn't hear it all the moment.
Slide rule. A slide rule. Right. So this is a chart that I got about the Nobel Prize winners in all categories as of the end of 2017. You see here lots of peace prizes. These are women, lots of peace prizes. Nadia Murray got it in 2018. I've added that one on there. Chemistry. Literature, of course, many women got Nobel Prize in literature. Usually that's a one-off, I think. Economic sciences, there was only one until this year when this young lady got it. She was the youngest economics prize winner ever. She got this for her essays on world poverty and how to eradicate world poverty. So in 2019, of the 14 laureates in all fields, 13 men and 1 woman. So you see that it's still an issue there. Physics is Marie Curie, of course, and Maria Gotha-Meyer. She was the one. Marie Curie got it in 1903, and then Donald Strickland came in 2016. I'll talk about that. Now, as it happens, there are 6 Swedish physics professors on the Nobel Committee, and this year one of them is a woman. But in recent years, 2 of the chairs of the committee have been females. I happen to know both of them. I've worked with one of them, but they didn't nominate any women at that time. So let's go back to some history. This is a rather brilliant woman, Emily de Tonillier de Rostoy de Châtelet. She didn't live very long. She died in childbirth, or after childbirth, at the age of 43. She was a high-born French lady. She was married at 19 to the Marquis, or Marquis de Châtelet, who was 34, quite a bit older. She loved studying maths and physics. She had a 16-year affair with Voltaire, famous, brilliant Voltaire, famous for writing Candide, but he was also did experiments with her. They had an affair. He lived with her in her chateau with her husband's permission, apparently, in her lab doing experiments in physics. He got wealthy and he bought a piece of land, Bernay. It was spelled F-E-R-N-E-X at the time, as lots of towns around there were Gex and Maisonnex and so on. I lived around there. But he changed the X to a Y, bought the land, and moved it into France, because in Switzerland they weren't allowing plays to be shown. So I don't know exactly how that worked, but it became part of France. And it was very near Cern, and I lived in Fermi Voltaire, as it's called, for a year. This is the chateau of Voltaire in Fermi. But this is Emily de Toniller's chateau. So one thing that she did was postulate the law of conservation of energy, the first to do that. She said if you include kinetic energy and potential energy, then that energy is conserved overall. So this was a real novel thing. Among other things, she had a theory of heat. She translated Newton's Principia, large tone, from English into French, and that is the only French translation of Newton's Principia today with a commentary. And apparently she actually made some corrections to Newton's. So this is, I put text here because I want to write a couple of things out. Okay, she conservation energy, proved much later theoretically by another great woman mathematician. Do you know who that was? The great woman mathematician who proved theoretically the conservation of energy. I'll get to it. This is a book on the nature and propagation of fire. And I will read. Okay, among other things she did, biblical scholarship. De Châtelet wrote a critical analysis of the entire Bible. The synthesis of her remarks in the book of Genesis was published in English in 1967. And a book of her complete notes was published in 2011 in the original French, edited and annotated by Bertrand Eugene Schwarzbach. Also, she invented financial derivatives, or something very close to that.
Oh, boo.
She was a gambler, you know, high society lady, went to casinos. She lost a considerable sum for the time of 84,000 francs, some of it borrowed, in one evening at the table at the court of Fontainebleau, to card cheats. To raise the money to pay back her debts, she devised an ingenious financial arrangement similar to modern derivatives, whereby she paid tax collectors a very low sum for the right to their future earnings. They were allowed to keep a portion of their taxes they collected from the king, and promised to pay the court gamblers part of these future earnings. So that was a pretty clever one. Actually, I did mean to read out, I skipped past, I go back a little bit, if you don't mind, to Maria Goffman-Meyer here, because in her Nobel lecture, I've got these lectures, which is very interesting. She wrote about her discovery of the nucleus. At the time, Enrico Fermi had become interested in the magic numbers. I had the great privilege of working with him, not only at the beginning, but also later. One day, as Fermi was leaving my office, he asked, "Is there any indication of spin-orbit coupling, meaning the spins of the protons and their orbits coupled together?" Only if one had lived with the data as long as I could one immediately answer, "Yes, of course, and that would explain everything." Fermi was skeptical and left me with my numerology. I do not know how many false starts my German colleagues made, but I had certainly made many. This one was not. The magic numbers from 828 on, due to spin-orbit coupling. In 10 minutes, the magic numbers were explained, and after a week, when I had written out the other consequences carefully, Fermi was no longer skeptical. He even taught it in his class in nuclear physics. Wow, okay. So now moving back forward. Okay. So, yeah, so who later proved conservation of energy? Yeah, notice she also died in her 40s, 1882 to 1935. So she was a mathematician, really, and she developed very advanced mathematics. Einstein says she was the greatest woman mathematician of all time. But she studied abstract algebra, other fields. This is her story. She did a dissertation at the University of Erlangen. Women were excluded from academic positions, so she did mathematics for 7 years without pay. But she was noticed and recruited to the University of Göttingen. But the faculty objected. Anyway, she went anyway and lectured under Professor Hilbert's name. He was her mentor. So she gave his lectures under his name, but she did not pay. Finally, at age 37, in 1919, she got paid as a Privatdozent, which is a sort of lowly sort of assistant lecturer sort of thing. And then in 1933, all the Jews from the university were dismissed by the Nazi government, kicked out. She came to America, to Bryn Mawr College, where she stayed in America. A former student of hers said, completely unegotistical and free of vanity, she never claimed anything for herself, but promoted the works of her students above all. Well, she proved mathematically that this is simplified, but it's not the Lagrangian, but never mind that. If a physics experiment does not depend on when you do it, other things being equal out in space, you do it here, you do it a year later, or 2 years later, and you get the same results, physics doesn't change with time, then energy must be conserved. If it doesn't depend on where you do it, here, there, over there, you get the same results, forgetting about other things like gravitational fields, which are external things, then momentum must be conserved. And if it doesn't depend on the orientation of your experiment, your lab can be this way, this way, this way. Remember, no gravity fields allowed, you're outside that. Then angular momentum must be conserved. And this is a relationship between symmetries. A symmetry is something which doesn't change when you change something. So, like a sphere is symmetrical because you can look at it any orientation, it looks exactly the same. These are symmetries in space and time and orientation, and they give rise to conservation laws. There was a Fermilab colloquium on 100 years of Nerva's theorem in 2018, and I put this link there because there are hundreds of outstanding talks on video there. We've been recording those colloquia for many years, and you can go and see them. Several by Nobel Prize winners.
My quick question.
Yeah.
Was she on the faculty of Bryn Mawr? I mean, was she accepted then? And
She was accepted then on the faculty. Yes, she was paid then.
It's a women's college, too.
yeah.
It's a women's college. Yes, okay. Yeah. So then I'm going back now in history to some other historical characters. Caroline Herschel. Now she didn't die young like the others do. She died age 97.
Good.
Good. The picture looks like she was 96 there in the picture. She was the first woman scientist ever to be paid. She was, and her brother, William Herschel, who discovered the planet Uranus, she came over to England from Germany to work as a sort of housemaid to her brother, really. But she was obviously interested in astronomy, and he got her paid as an assistant to her. He wasn't called Astronomer Royal then, that term came later, but he was the king's astronomer, if you like. Well, comets were seen as very important, of course, and she worked on discovering comets. In order to find these comets, she needed to know about other little patches of misty light in the sky that weren't moving. They were the background to her search for comets. And she catalogued over 2,500 of these. They turned out to be nebulae, many of them galaxies, some of them are gas clouds. But only 100 were known before, and she catalogued these, and she got the gold medal of the Royal Astronomical Society. But her motivation was not finding galaxies. We didn't know about that until maybe the Hubble much later, but she discovered 8 comets, which got her sort of famous. Mary Somerville, the Somerville College in Cambridge, I think. Anyway, she also died in her 90s. She studied maths as a girl, but her father discouraged her from doing that. She said, you should not do that, you should do making or sewing or whatever. She married William Somerville, and he supported her, and she was very intellectual. She hosted an intellectual circle in her house. It included Charles Babbage, who invented this computing engine, the astronomer John Herschel, who was her nephew, actually William's son. But she did experiments herself on magnetism, wrote about physics and astronomy, and she translated from French to English a book by Laplace, Mechanism of the Heavens, which became a major textbook. So that's Mary Somerville. Then there's Maria Mitchell, also in the 19th century, who was an astronomer. You see the telescope there. She was the first, again, she was at Vassar College. Is that a women's college? I know. First female astronomy professor in the United States. Her father taught her how to measure star positions. His job was testing the accuracy of chronometers and using star positions to test that for the Nantucket, Massachusetts whalers. And she helped him. She helped him time an eclipse when she was 12. And at 17, she started her own school for girls, teaching science and maths to girls, which was sort of unusual at the time. When she was 29, in 1847, she discovered a comet which made her world famous. She was American. She was married to Herschel, who was British. She was the first woman elected to the American Academy of Arts and Sciences, and she got a medal from the King of Denmark. She became pretty famous by discovering that comet, which became a naked eye comet. But she continued to study the sun. She travelled 2,000 miles to see a total solar eclipse. That's Maria Mitchell. Now here we come back to Marie Curie. Okay, everybody knows Marie Curie. So she was born in 1867 in Warsaw. When I was in Warsaw for a day, I visited her house. It's now a museum, very interesting. And she got the Nobel Prize in Physics in 1903. She was the first woman Nobel laureate, with Pierre Curie and Becquerel, her husband. Before she came, she was a private tutor looking after her elder sister and her father. Her sister came to Paris to study medicine, and she wanted to go, but she had to stay behind, and she got a job tutoring, and she looked after her father, and only later, after her sister finished her studies, I think, did she go to Paris and start studying science. She said it was like a new world opened for me, the world of science, which I was at last permitted to know in all ability. She had to overcome huge barriers, of course, but she was eventually accepted and famous. Well, there's so many stories about her. What was her main characteristic, do you think, that actually helped her?
She had a glowing personality.
She also had a lot of curiosity. Henrietta Swan-Leavitt, you may have heard of her. There's a play about her recently, actually. So she was an astronomer. She was an assistant, actually. She's got a job measuring glass plates of the stars on, and noticing certain stars are variable stars. They vary periodically, and there's a type called the Cepheid variables from the constellation of Cepheus, the whale, I think. Anyway, this is a characteristic brightness curve of one of these stars. They fade, and then they suddenly brighten, and they fade and brighten over a period of days. And what she noticed was, by looking at several of these that were about the same distance, I think they were in the Meteorite cloud, so all about the same distance, there was a relationship between the period of their oscillation, of their brightness changing, and the brightness. So that's this graph on the right here. You see, this is the luminosity, the brightness, if you like, and this is the pulsation period. And the longer periods have higher brightness. So that relationship, she got and discovered that relationship. And that means that if you now look in the Andromeda Galaxy and you see these stars over there, and you measure their apparent brightness, you can get the true brightness. And the apparent brightness tells you the period, that gives you the distance to them. So then she showed the Andromeda Galaxy is actually very, very far away. It's not something, a cloud inside our galaxy. So she set the scale, the distance scale for galaxies. Harriet Brooks, she was a graduate student of Ernest Rutherford in Canada. Rutherford, who was born in New Zealand and ended up in England, but on the way he went to Canada, McGill University, and she was a student of his. And he said, thorium is emitting an emanation, he called it. Is it a gas or a vapor or a powder? He asked her as a student to study it, and she showed that it was a gas, and it's a gas actually radon, showing transmutation of elements. So thorium turns into radon, and that the particles emitted, the so-called beta rays, were the same as J.J. Thomson's electrons that were discovered in 1897. So she showed that these particles that are kicked out of nuclei, that are radioactive beta decay nuclei, are the same as the electrons you get out of a cathode in the conduction of gases that J.J. Thomson showed were particles, the electrons in 1897. The year my father was born, actually, believe it or not. So then she went to Cavendish with J.J. Thomson, and several single orbit papers were overlooked. One paper with Rutherford, but she measured the decays of nuclei and showed the exponential decays with different lifetimes of these different radioactive isotopes. But she was extremely modest, apparently had low self-esteem, said, I'm afraid I'm a terrible bungler in research work, but Rutherford was impressed. There was pressure for women in their 30s to marry and have children, and that's what happened to her. So she didn't do physics beyond that time, I think, when she married and had kids. Now, Lisa Meitner, she's a terrific classic of who should have got the Nobel Prize and didn't. This is her in 1906, 1946. So she was a respected professor in Germany. Here she is collaborating with chemist Otto Hahn, I say nuclear chemist because he would study radioactive isotopes but with chemistry, chemical properties. And he wanted to make elements heavy in uranium by bombarding them with neutrons and hoping the neutrons would stick. make elements heavier than uranium. She worked with him, it was her lab in Germany, but being Jewish, she had to escape Nazi persecution in the 30s and fled to Sweden, where she got a job in Lund, I think, but the head of that was Manus Sieber, and he was not helpful to her. He gave a junior assistant salary. I don't know if he was anti-Semitic or not, but he was probably jealous of her and didn't help her. And then Hahn, her colleague in Germany, who was still there, wrote to her saying he was puzzled by some findings, chemical findings that seemed to be something that had the properties of barium in the debris, which was incredible. And Lisa Meitner in Sweden in December in 1938 was on a walk in the snow discussing with her nephew, Otto Frisch, who was also a physicist. And suddenly she had the brilliant idea that actually what was happening was that when the uranium is hit by a neutron, it can split in two, release more neutrons and energy, because the nucleus is very unstable. It's hit by a neutron. So there's nuclear fission. So she realized that. That was astonishment to Fermi, or Rutherford already just died. Of course, the result of this discovery of nuclear fission was not only all the nuclear power stations we have and nuclear weapons, which she refused to work on. And then, just at the 1944 Nobel Prize awarded to Hahn in chemistry, she didn't get the prize, and I think it's because Manus Sieber and Blackpool, he was on the Nobel committee, of course. So that's a really very shocking story, really. And I think also Vera Rubin, who died on Christmas Day 2016, should also have got the Nobel Prize for an astronomer for discovering dark matter. We still don't know what that is. A woman's place in the dome, she questioned. She was a great astronomer. This is her recently. So what she did was measure the rotation curves of galaxies. So you look at a galaxy like this, and you can measure the speed of stars coming towards you or away from you. If they're coming towards you, they look slightly bluer, away from you slightly redder, which is a Doppler shift. It's like a car going by. High pitch, low pitch, but with light. And by measuring the red shifts and blue shifts of stars, you could show that galaxies are rotating, stars are going around. Actually, the last time we were in this part of the galaxy, after one revolution ago, was when the dinosaurs were roaming the Earth. It takes a long time to go around. But she measured the velocity, it's kilometers per second of stars, as a function of distance from the center. And you'd expect it to fall off as you get further away from the center. The mass is concentrated where the light is. But actually, the rotation gets higher and gets higher. If the only matter in the galaxies was the stars and the planets, which is not much compared to the stars, and gas and dust, then the galaxies should fly apart if they're spinning. They should, centrifugal force would throw them apart. And she measured hundreds of galaxies like that. And she showed there's about 5 times more matter than we actually know about than in stars, planets, etc. And this is dark matter. We think it's made of particles still to be discovered. We're searching for it at Cern and Fermilab and so on, haven't found them yet. She received many honours, National Medal of Science, Gold Medal of Royal Astronomical Society. She didn't get the Nobel Prize, which just goes to show. And oh yeah. So I've got a bit more about her here. Signing up. She was born in Pennsylvania in 1928, daughter of Jewish immigrants from Poland. She developed an interest in astronomy at age 10, built a crude telescope. She was advised by a high school science teacher to drop science and become an artist. She earned a bachelor's degree in astronomy at the all-girls Vassar College, and her application to enroll in the graduate astronomy program at Princeton was turned down because of her gender. That was their rule for another 27 years. She went to Cornell and earned a master's degree, studying the motions of 109 galaxies and finding deviations from Hubble's law, Hubble's flow. She was 23 and pregnant when studying for a PhD at Georgetown University, the only one that offered a graduate degree in astronomy. Her thesis gave the first evidence for galaxy clusters. Throughout her graduate studies, she experienced discouraging sexism, including an incident where she was not allowed to meet with her advisor in his office because women were not allowed in that area of the university. That's very real. And I think she really, obviously she should have got a Nobel Prize. They gave it to dark energy, which is much less certain than dark matter. Now, Jocelyn Bell Burnell, who is still with us, born 1943. I put this star against 10th of July because she's 2 weeks older than I am. 23-year-old graduate student at Cambridge, UK. She studied radio telescope signals as a graduate student, and in November 28, 1967, noticed some scruff repeating in the charts on the chart traces. Every 1.33 seconds. Tick, 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 tick. And then, of course, you have to study what is it? Where is it? Some interference, some radio signals from some. She showed that it actually follows a point in the sky, you know, because she showed, and it turns out to come from Crab Nebula, and it's a pulsar, a compact neutron star, 100 trillion times denser than iron. Okay, well, actually, you can work that out for yourself if you just remember two numbers. Typical size of an atom is about 10 to the minus 8 centimeters. The typical size of a nucleus is about 10 to the minus 13 centimeters, 10 to the minus 14 centimeters of iron. And that's a factor of 10 to the 4. For volume, you cube it, so you get 10 to the 12, which is 10 to 12. That's a billion, that's 100 billion, 100 trillion. So, trillions, billions, big numbers. But her supervisor got the Nobel Prize, Jewish, and wow, she really wasn't included, and should have been included. Anyway, last year she got a special breakthrough prize of $3 million, which she's donating to help women and ethnic minority and refugee students become physicists. So here's a diagram of how the pulsar works. It's a neutron star, which is actually about 2 or 3 kilometers across, as dense as the atomic nucleus, and the spinning, in this case, spinning every 1 1/3 seconds. So it's spinning very fast, but it's magnetic. It's got a magnetic moment, magnetic. It's a magnet, but the magnet is not aligned with the pole, like the Earth's magnet is not quite aligned with the pole. And as it spins, that magnetic field generates optical signals. This is the Crab Nebula, where that pulsar was found, discovered in 1732. Doctor, an 1840 drawing by the Earl of Ross said it looks like a crab. That's how it got the name. And there was supernova seen by the Chinese back in 1054. The star exploded a long time ago, but we saw it, the Chinese saw it in 1054, it was there. And now this is a picture of it, superimposed optical and X-ray emissions, beautiful picture, X-ray picture and optical picture superimposed. And you can see that with a small telescope if the sky is not too polluted as it is here. Now Nancy Roman, she was an obituary in New York Times in 2018. She formed an astronomy club when she was 11 with friends, PhD in Chicago, and then she became NASA's first chief of astronomy. And she worked on the Hubble Space Telescope, organizing and convinced Congress to pay for it and so on. So the Hubble Space Telescope, we can thank her for a lot she did for that. And here is a picture from the Hubble Ultra Deep Field. So the Hubble Ultra Deep Field, that was brilliant because you've got this space telescope up there. Now, Hubble was from Wheaton, right? Anyway, the director of the program for the telescope was apparently given carte blanche. He's got so much time, whatever it was initially, 100 hours or something, he could do whatever he wanted with it. So I'm going to point at a little piece of the sky where we don't have any stars, no stars in our galaxy, so we're looking out beyond the galaxy and taking a long and long exposure with this digital camera that's this size, you know, compared with what you have on your iPhone. And this is the sort of picture you get. This is a tiny patch of the sky. None of these are stars in our galaxy. They're all galaxies outside. You see some obviously galaxies, but all of them are galaxies. All of them. And if you multiply that out by the area of the whole sky, you conclude that there's something like 100 billion galaxies in our visible universe. 100,000 million galaxies. And each one, one's like ours, about 100,000 billion stars in. So 100,000 billion, not 100 billion. Well, there are many amazing women in STEM now, of course, and as I said, there are about, the project I'm on at Cern, the Large Hadron Collider, there's a total of about 4,000 physicists and engineers on it. and I think there must be about 800 or 900 women there. These are a few physicians of prominence, I would say now. Gabriela Gonzalez. She's a spokesperson for LIGO, which detected the first gravitational waves from colliding black holes and spiraling and merging. As these black holes orbit each other like that, they radiate gravitational waves, and like a charge would, if you spin a charge, would radiate electromagnetic waves, gravitational waves, and as they do so, they lose energy, spiral in, and then go as a sort of chirp. As they rush around each other and merge, that chirp signal is a signature of the gravitational wave merger. And the first one is like 1.3 billion light years away, and it was two black holes of masses of about 40 or 50 solar masses, and many solar masses worth of mass was turned into energy. And we detected that. That's an amazing story in itself. And Fiona Harrison, the leader of the Nuclear Spectroscopic Telescope Array, studying X-ray, supernova remnants, neutron stars, and massive black holes, and so on. But there's so many. And now, you may have heard of Fabiola Gianotti. She was one of the Women of the Year at times. She's the Director General at Cern. There are 10,000 physicists from all over the world working there, over 100 nationalities. She said she was inspired by Marie Curie when she was a girl. She was elected spokesperson of this project Atlas. There are two big projects at the Large Hadron Collider, Atlas, which she directs, and CMS, which is one I'm on. Fermilab is involved in that one. And we jointly discovered the Higgs boson in 2012, which was leading Atlas at that time. Now, she's not content with the Nobel Prize because far too many experimenters were involved in that discovery to give it to only 3, and you can only go to 3 people in a physics prize. So theorists, 3 theorists got the prize for the Higgs boson. What she said was, I cannot say myself that I ever felt discriminated against. Perhaps I was, but I didn't realize it. She's helping break down the barriers the male-dominated field created for aspiring female scientists. Specifically wants to give women more support when having children. She never had children. She was just too busy, focused on it. And she now regrets that decision. But it's not so easy to have children and keep a relationship like that. So, as I said, the top quarter at Fermilab is 1995. Higgs boson at Cern 2012. They're both Nobel-worthy discoveries, of course, but you can't give them to the experimenters because you can't say it was critically for this person or that person. So nobody got the prize for the top quark. 3 is a maximum on the physics prize. The W and Z boson discoveries, which were back in 1984, were given to two leaders of those projects. Well, one was the Vandermeer, who was a brilliant accelerator physicist who understood how to cool antiproton, make antiproton beams. And the other was Carlo Rubbia, who led the experimental team. But the Nobel Peace Prize is given to organizations, so I suggest that Fermilab and Cern would get it for international collaboration, peaceful collaboration. And I wrote about that in Positive Naperville, December 2018, on this little column called Peace on Earth and Goodwill to All. Wait, you may be thinking, I thought this was a science column. What does science do with peace? Those who visit Fermilab or Cern understand that and there are many international organizations, these partners inspired by Cern's success. Read about that. So then at last, in 2018, Donna Strickland broke the drought of female Nobel Prize winners in physics. She attended McMaster University, did an engineering physics program, including lasers, and studied lasers. She was 3 women in a class of 25, which is typical. And when a graduate student, she found a way to make ultra-short laser pulses. Again, chirp, like that. Tabletop, and this was a tabletop experiment. You had laser pulses, but she was able to make them extremely short. I've got another slide about that. Her daughter Hannah is a graduate student in astrophysics. So there's a clever technique she invented to increase the peak power of lasers. Previously, the limitation was that you had gigawatts per square centimeter, which would damage the amplifying part of the equipment. But she stretched each laser pulse in time and wavelength, amplified it and compressed it. And these are pulses she could get out. This distance between two pulses is 125 picoseconds. Well, in 2 picoseconds, light travel is 0.6 millimeters, so you can work out that's about this much light travel time between them. But the resolution of this is like 2 picoseconds. And it has applications in eye surgery, micromachining, laser cutting, and so on, fundamental optics, pushing the boundaries of ultra-fast pulses to ultraviolet infrared ranges. Now, she wasn't a professor when she did this. She only applied for a professorship after she got the Nobel Prize last year, and got to the University of Waterloo, the first full-time woman professor there. So, annually we have this International Day of Women and Girls in Science. It's the 11th of February 2020, United Nations headquarters. Let's celebrate this in our schools. Our schools should be celebrating that women and girls in science. Okay, that's a heads up on that. And NASA's launching an astrophysics Barbie. And I'm wondering what is this thing here? Wow.
Her telescope's pointed the wrong way.
It's also looking down here. He's studying micro. Anyway, yes. So thank you. So I have a question.
Did Curie get a Nobel Prize in physics and chemistry? Is that?
Marie Curie got one in physics and in chemistry.
Yeah, that's my question.
And her daughter got one too in physics. Actually, Irene Curie got it. So between mother and daughter, they got 3 Nobel Prizes.
And did the elder one die of contamination of radiation?
Marie Curie, she died of cancer eventually, and it's supposedly, yes, she probably, that was probably brought on by some radiation. In those days, you played with this stuff. You didn't realize how dangerous it was. But of course, radium, when it was discovered by her, I mean, she got tons and tons of pitch blende, which was dredged from mining and so on. And she would dissolve it in acid and stir it in barrels, and she was doing this, stirring it, and trying to eventually distilling it, because it showed some radioactivity, but a little radioactivity, because it had uranium salts and stuff in it. But she eventually managed to separate out this extremely radioactive part of it, which was radium. And radium was, you held it in your hand, it was warm, it was emitting heat, amazing. And then, of course, it was a sensation. You know the stories about the radium watches and radium girls who were painting these luminous dials with radium paint and zinc sulfide, told to lick the brush when it brushed stuff out. None of them died of cancer. So Marie Curie did die of cancer, and probably it was radiation, but it took a long time. She became very famous.
But Pierre died of cancer. He used to do part of the tricks with the radium there. He used to carry around his best knife.
Wasn't he also injured by a cart? He was.
Yeah, Pierre Curie was killed actually by a horse carriage. He was run over by a horse carriage on the streets. That's very early, I think.
There was an interesting article this week talking about a newly discovered magic number. Have you read about that one?
No.
I believe it's 38.
What element is element 38?
Magic number?
What is the element corresponding to 38 protons? I don't know, I haven't read about it. Okay. I don't know. I'll check it out. So you see, here's another story about magic numbers. The atomic structure had magic numbers because, you've got hydrogen, this one proton with 1 electron going around it. Helium's the next one, 2 protons, and it usually has 2 neutrons, and 2 electrons going around it. The 2 electrons can be in basically the same inner orbit because they've got the spin, or magnetic moment, and one can be pointing up, one pointing down. So those 2 are allowed to be in the same place. These particles with half-unit spin are called fermions, after Enrico Fermi, and you can't have 2 fermions with the same quantum numbers in the same position. So 2 electrons can only be in the same orbit because one's pointing up, one's pointing down. But then that orbit is full. So the next element is lithium, number 3, and that has got one more proton, therefore one more electron. But that electron can't be in the same inner orbit. It's full with those two. It has to be in a higher up orbit, which is larger. So the lithium atom is quite a bit larger than hydrogen. But if you knock off the outer electron from lithium, it becomes an ion. 3 protons, but only 2 electrons. And that ion is actually surprisingly smaller than hydrogen, because the nucleus has got a higher electric charge, the inner orbit is closer in, so the lithium ion is smaller than the hydrogen atom, which makes it easy to embed it in an anode of a lithium-ion battery, which got a Nobel Prize in chemistry just last month. Okay, these physicists who developed a lithium-ion battery. So you've got this, and it works because the lithium-ion, well, partly because the lithium-ion is smaller than hydrogen, and easily embedded in the metal, and then pulled out again, embedded in the metal. It's got energy there. You pull it out, and it uses energy and makes the battery work. So that's interesting, right?
Can you go further? Now, my chemistry in 30, 40 years ago was understanding that there's the first shell with 2 electrons, and then it goes to 8 electrons in the next shell. How do those electrons coordinate?
Right.
So
The
that there
next
can
shell
be
has
8
8 electrons, you're right. And they're in pairs with spin up and spin down, so 4 pairs. And those 4 have got a different quantum number, an orbital quantum number, so that you're allowed to have 8 in the second shell. And Maria Koppelmeier applied the same sort of principles to the nucleus. But the lithium, so...
Is it because they're farther away from the nucleus that there's different controls on them? Or talk more closer to the microphone, too, maybe.
Yeah, okay. I don't know.
Okay.
I can't simply explain the 8 in the second shell. It's a question of orbits. Why there's only 2 of the inner one and 8 allowed on the next one, maybe.
It's the degrees of freedom allowed for their orbital angular.
What degrees of freedom for orbit alignment? Yes, that's right. So actually my November science column is called Hydrogen, Helium, Lithium, Energy, because of that prize for the lithium-ion battery. But hydrogen, of course, is the most abundant in the universe and is fueling the sun. Our solar power comes from hydrogen fusion. Helium was made in the sun and was discovered in the sun. And now lithium-ion batteries enabling us to use solar power because we can store the solar power in lithium batteries and use it at night. And then burn the cell phone to it. So the lithium battery is very important for energy and for renewable energy. Yeah. Other questions? Yes.
Did I hear you say, I think I heard you say that you, with the collaboration thing, that you wrote an article that maybe that there could be a peace prize for collaborating among scientists? Is that what you said?
Well, this is just me.
I know.
Yeah. I'm saying, so I argue, because the Peace Prize is given to organizations as well as individuals. And it can be given to like the World Health Organization or UNESCO or something like that. And I would argue that particle physics research and big science research brings together people from all nations working together collaboratively and shows that that can be done, And I was on an experiment at Cern 35 years ago with people from China and Russia and America and Israel and European countries all working together peacefully.
Right.
So I think that big science is a serious force for peace in the world. I mean, at Cern, it's mainly you go to the cafeteria at Cern, you see people from all over the world. It's not just Europe anymore, it's the whole world, basically. And so I would say that Cern and Fermilab could share the Peace Prize, all right?
Well, that's what I thought I heard you say, and then you said the response was, what does science have to do with peace? I just think that's a sad response.
Oh, yeah. No, what does science do with peace was the title of or the lead of my story.
Oh, I thought you said you got
because people, what's science to do with peace? Well, it's got a lot to do with peace.
Okay.
This is sort of my rhetorical question. Yeah. Okay.
Here you go.
Ada Lovelace,
Ah.
you hadn't mentioned her.
I didn't mention her because she built computing, she built computers, right? But she wasn't a scientist in that sense. She didn't advance science, except we didn't build a new computer to advance science, yeah. And of course, there were many that I didn't mention. I think Lovelace was key in development of computers.
There was a woman, Leona Woods, who worked with in Chicago on the atomic project. I worked with Enrico Fermi. She was born in 1919 in LaGrange, Illinois, right here, and initially was denied any progress in a PhD program in physics, but eventually she did, and she got a PhD from the University of Chicago. And she was the only woman of the 7 people on the team that worked on the original Chicago pile number
Okay.
1
Yeah.
and all that. It was fascinating to me that she was born right here in LaGrange.
I didn't know that, yeah. And that first atomic pile, which by the way, that, Fermi and collaborators, including this young lady who built this pile in the squash courts of Chicago, and it's the first nuclear reactor, and they damped it down when it was emitting about 30 watts or something. They were worried about it. So that was that, and that was
A fun fact, I was conceived a year from that experiment in the squash courts, about 10 miles away.
Yeah.
So that seems to me that's an irresponsible experiment to be doing in the middle of the city of Chicago. Everyone said, oh, he knew what he was doing. He's running an experiment. If you knew how it was going to come out, you wouldn't have to run it, right?
Well, he had a lot of students on top with buckets of barium loaded water to throw them in.
And he had to scram that too. With the,
He had a slide rules. He had a slide rules. Yeah.
But I'm here, so
May have had some outcomes that we don't know yet.
yeah.
That's why I have curly hair.
Thanks so much, Mike. Very nice. Appreciate it.